Dear students, so now we are going to proceed to the concluding part of the module 3. We will be discussing the rheological application. The rheological application, you must be aware, in chemical engineering you have taken up subjects in your core curriculum like fluid mechanics, then transport phenomena. So, we will not discuss much about the details of the fluid properties and the other rheological properties, but we will touch on them, and our main aim is to how to use the instrument to get important properties which are useful in the case of fluid. So, we will start today with the rheometer. Mainly we will see the application of rheometer and its concerned fundamentals along with the concepts. So, this is the 5th lecture within module 3. So, what we will be covering up in this particular lecture? We will be covering the concepts of stress and strain, the constitutive relation, and then finally the rheometers and the measurement techniques. In the rheometer and measurement techniques, it means what we do is that you must be knowing that, I mean, in the case of viscosity, you actually measure either shear stress or shear strain, and from this shear stress and shear strain you may get the viscosity. Okay. But does the particular instrument measures directly, or there is an indirect way of measuring? So, that we will see what are the different way we can measure this rheological properties, and an important aspect which we will cover is the geometrical arrangement. Okay. The geometrical arrangement of the viscometer. Okay. So, let us proceed. So, what is rheology? Rheology is the study of matter's flow and deformation. Okay. Matter's flow and deformation. This matter can be either a solid, as a liquid, or a gas, anything if it flows. So, it means that if it flows, obviously how it is going to flow, and if I provide an external force, how it going to be deformed. So, entire this domain or this entire science is called rheology. So, Professor E.C. Bingham of this Lafayette College in Indiana, they invented the term, actually he coined the term rheology in the 1920s. So, what is flow? Flow is nothing but it is a type of deformation. So, when something flows, we say a liquid is flowing, or you may have a gas which is flowing. So, it is being deformed as it goes or it flows. So, some of the deformation relationships are obviously related to the material. So, the particular material will have different resistance to flow. So, in this case these are actually quantified in these two terms, viscosity and modulus. Viscosity is nothing but stress by shear rate, and modulus is nothing but stress by strain. So, my question is, we not discuss these in details, because I suppose you must be knowing this definition, but to actually summarize, viscosity is usually related to liquids and modulus is usually related to solid. Okay. So, it means that if some material has both this viscous as well as modulus part, we call that viscoelastic. Viscoelastic. So, it means it has a flow behavior corresponding to liquid and a flow behavior corresponding to elastic. So, what do you mean by elastic? Solid material, suppose you have a solid material, you pull it apart from both ends. So, if you release the force, it will come back to its original position. So, how much it can stretch and what is the force applied, that is coined using modulus, and this is given by stress and strain. Viscosity, you know, it is very simple to calculate. You just calculate the force and corresponding stress per unit area, and you divide it by the shear rate. So, for Newtonian fluids, you know, it is a straight line. Shear stress to shear strain is a straight line. So, we will see what we have. So, for example, if this is a simple shear flow, so you have a liquid which is flowing in between two fixed plates. So, bottom plate is a velocity v0, while the top plate is having a velocity v0. So, it is v0, I mean this v0 is actually stationary. So, the bottom plate is not moving, and v0 is some value. Okay. So, we should not confuse this 0 and v0, and the force is generated while the liquid flows from here. So, those liquid fluid elements which are into the vicinity of the bottom plate will be having a lesser velocity. So, those which are actually attached with the bottom plate is having almost they are at rest, and as you go in the increasing y direction, the velocity of the elements of fluid increases. So, this is increasing. Okay. So, what is it then? What is a shear stress? How do you define a shear stress? Shear stress is nothing but the force per unit cross sectional area. Okay. And shear strain, if you want to in percentage, you just multiply by 100. So, it is nothing but it is x of t. It means how much of distance it has moved in the x direction with respect to temperature divided by the width between the two plates. This is called shear strain. Then shear rate is nothing but you divide this with respect to time. So, it will become shear rate. So, it is per unit second, because you do not have the units here, it is dimensionless shear strain. And the viscosity obviously is given by this expression. You have the shear stress with respect to shear rate. So, this you get for a viscosity in Pascal into second. Okay. So, this you must have read in fluid mechanics. I am not going into details. So, but in the case of rheometer, the instrument, I mean, you should be aware that the instrument which actually measures the viscosity is called rheometer, or sometimes a simple form of design you call it as viscometer, redwood viscometer, you know. That is nothing but you just measure how many drops of the particular liquid is falling through a particular channel, and you measure that time. So, from there also you can get viscosity, but rheometer what it will do? It can measure viscosities of various ranges from viscous behavior, the elastic behavior, and other properties. So, what are those properties and how it measured? We will see, and what are the geometrical configuration inside a rheometer. So, this is a rheometer. So, here you have a motor, this is a flow diagram, this is a motor, and these are the two fixed plates, and in between you have the liquid being sandwiched. I am considering here liquid. You can consider some material which may be liquid as well as solid, it's you can assume, but here we are considering liquid. Now, just visualize, this is the top part, this is the bottom part. Okay. So, when the upper part these moves, and if you keep this as stationary, the lower plate. So, what it will do? Initially, let us say the liquid is here, you have to just visualize in a 3-dimensional manner, then only you can understand. So, the liquid particles, when you rotate this in this direction with a velocity, angular velocity in radians per second. So, this you can, this is predefined, you can set it in the rheometer. So, if you apply this, keep this stationary. So, what it will do? The fluid particles will move in the 3-dimensional manner, in this manner, this way. So, the one which is attached to the bottom plate, like I was showing in the previous slide, it will be almost be at rest. Likewise, you will have a velocity profile which increases as you reach to the top of the plate. So, if h is the distance between the two plates and theta is what nothing but the angular motor deflection. So, this may be this particular value theta. Okay. How much is the theta value? Then what it does is the rheometer calculates these properties based on these formula, that is stress. What is stress? Stress is nothing but 2 pi r cube into m. M is the moment of inertia in micronewton into meter. Then strain is r by h into theta. What is r? R is the plate radius. So, this is the r, the plate radius. Okay. So, these are both are same, this is r. So, you need to know r, you need to know h, you need to know the angular deflection theta, and you need to set up the motor angular velocity. So, if you do that, you will get strain in this way, and you will get strain rate, you get r by h, which is a constant. So, you can fix a particular strain rate, because r and h are constant, they will not change with the condition, but you can vary this angular velocity. Okay. So, if you fix a particular strain rate, you can calculate strain, and with strain you can calculate, you can calculate stress, and with stress you can calculate strain. So, this is how you call it a flow in a parallel plate. So, these are type of configuration is available in the rheometer. So, what does the rheometer do? Then finally, a rheometer is a device that may be used to determine the viscosity of fluids, semi-fluids, semi-solids and solids. It may give information on the material's properties. What are the properties we are talking about? primarily viscosity, which is defined as a material's resistance to deformation and is proportional to the shear rate or shear stress. So, this is quite obvious from the fundamental equation. We know that viscosity is directly related to the shear rate or shear stress. So, now this viscosity obviously depends on both time and temperature, because if you increase the temperature, your viscosity will change, and if viscosity changes, your shear stress is also changing. Then the third part is the most important part, because many of the materials we prepare has both a liquid like behavior as well as a solid like behavior. Those are called viscoelasticity or viscoelastic fluids. So, that refers to a material's attribute of being both viscous and elastic. What are these? G prime, G double prime, tan alpha. We will be seeing this in detail later on, because this G prime is, these are two G prime, these are values which actually record the magnitude of the elasticity, elasticity and viscosity within a material. So, they call sometimes these are called as loss modulus and storage modulus. So, loss modulus means viscosity, it relates to viscosity, and storage modulus means it relates to elasticity. The term storage means it has that amount of elasticity. So, it is storage modulus. Tan alpha is nothing but if you divide these two terms G prime, G double prime, you get the tan alpha, which is nothing but loss tangent. So, these are very important properties to characterize viscoelastic fluid. So, these can be done in a rheometer. Ultimately, so if to summarize, what do we do in the rheological domain? Like I described, in a rheometer, it can study the matter flow and its deformation. It can do a stress analysis, which is nothing but force per unit area and its relationship between deformation. So, the stress with respect to strain or stress with respect to strain rate, either way you can get this variation. What does it measure? It can measure torque. Torque is indirectly you want to measure force. It can measure the angular displacement. It can also measure the angular velocity. So, it can measure all these three things, torque, angular displacement, angular velocity. Now, let us see in details. So, how we can use a rheometer? This is very important. So, we can use a rheometer based upon our need. So, whether it is we want it to flow or we want it to not flow, not deform easily. So, we can either check how far it deforms when it is pushed, or we can provide the force. Whenever I am talking about force, it is actually torque. You can set torque in the rheometer. So, actually you set up the stress basically, and so if you provide torque, you can measure what is strain. Strain directly you cannot measure, so you will measure angular displacement. Then you use the equation which I described the two slides before to get the strain, or you can provide the strain. So, if you fix a particular angular velocity, that is you are fixing strain, you can measure stress. So, either way you can do it, either you apply stress, you measure strain, or you apply strain, you measure stress. So, this is actually the diagram of a rheometer, which is there in our analytical laboratory, which is housed in our Department of Chemical Engineering. This model is based on the company which is called Anton Par, which are the leaders of this particular rheometer. So, these are the different menu, these are the different digital platform where you can change the specification. So, you see that this is the actually your motor, fine, this is a motor and you have a sensor below, fine. So, you have a motor here, sensor below, here you actually let us say if I am talking about parallel plates. So, this parallel plate is nothing but you get this part, you lower it down to this particular bottom plate which is fixed. So, and you spread a liquid like this. Now, when you spread a liquid like this, then after that you can set this different way. Either you can pre-insert torque, you measure strain, or you pre-insert stress or torque, you measure strain, or provide strain, you measure stress, either way. So, how is this calculated in a rheometer? In any rheometer, the stress is usually calculated from the torque. The formula is this, m into c. What is this m? M is the torque in Newton per meter. Okay, so, stress is dynes per centimeter square and c sigma is the stress constant. So, this stress constant obviously is a quantity that is geometry dependent. So, several manufacturers have a different way to compute this geometry dependent stress constant values, because it will not give directly stress, because these are some instrument factors which has to be taken so that you get the correct value of the stress. So, this if you notice carefully, this is the circular plate which is kept in motion. Then comes the angular displacement. Is when you want to calculate shear strain, what you do is the angular displacement is applied through the rheometer in a generic rheometer. So, it is applied through the rheometer in any generic rheometer. What it is expressed as again is a product of a strain constant into theta. Theta is the angular motor deflection strain constant. Again this is dependent on the geometry, strain constant is geometry dependent factor. So, now for example, if we want to talk of solid, the solid means you have one rheological parameter, that is the modulus, nothing but shear stress by what is it? This is strain, shear stress by shear strain, which is the constitutive relation which you have been reading in fluid mechanics. Then this is the uncorrected rheometer measurement, okay. This is the uncorrected ones multiplied by the correction factor. So, this is the way it calculates the modulus primarily for solid like material, okay. So, rheological material, rheological parameter is equal to constitutive relationship, which is equal to an uncorrected rheometer measurement into the correction factor, okay. Again the angular velocity in a generic rheometer, angular velocity is again directly recorded and the shear rate is obtained through this formula, where gamma dot is shear rate, again this is the shear constant and angular velocity is in radians per second. So, this strain constant again is a geometry dependent factor. So, you see this angular velocity, shear rate, shear stress all are dependent on the geometric factors. So, if I want to discuss the viscosity, so again you see viscosity is a liquid like property, is nothing but constitutive relationship shear stress by shear rate, and you have m by this which is the uncorrected reading, this is the motor velocity, angular velocity, torque, and then you apply the correction C sigma into C. This is the way most of the rheometers work. Now, what to use when? So, we have different arrangement, these all are different arrangement, this let us say this is arrangement 1, arrangement 2, arrangement 3, this I am not showing, arrangement 4, okay. So, if you have low to medium viscosity, what you do is other two arrangement may not be efficient to capture the viscosity or the rheological properties, you use a concentric cylinder. What it is, you have a cylinder inside a particular enclosure, so this is connected with the motor, okay. So, you have the liquid, you keep the liquid inside here and you rotate, provide a angular velocity such as water. But if you have low to high viscosity, then cone and plate is better. What is this cone and plate? Means this particular motor is connected with a device which is cone, although it looks like this, but the angle is very less. What is the angle? It is depend upon this angle. So, this angle, based on this angle different cones are available, okay. So, now it is which we have in our laboratory here at our institute is only 1 degree. So, even if I show you, you will never able to see the actual cone dimension. So, something like that. So, you fill the liquid here. So, there is a small gap here, it is not visible here, but it is there. So, you have liquid filled like this is for very low to high viscosity. Now, for soft solids you can prepare a parallel plate, soft solid like gel like solid, you can prepare the parallel plate, okay. So, the parallel plate is just now I discussed. Then torsion rectangular means very high values of viscosity, not we do not tell viscosity, it is actually elasticity, is nothing but you have this type of structure, you have seen one way here and you have another way here, and in between you have the material, let us say it is steel, okay. So, obviously you pull up in the both the different directions and you measure the total force along with that area and what is the elasticity or the modulus. So, this is steel, torsion, rectangular. So, it means that we can use different geometric configuration for measuring different various types of viscosity. So, now how to decide on the size of the geometry? Okay, you have discussed the different geometrical arrangement. Now, if you suppose you discuss different, suppose you narrowed your choice to parallel plate. Now, if it is parallel plate, what should be the diameter of that plate? Okay, and what should be the height of the liquid? So, for that you should observe the viscosity of the sample first. I mean, you can measure the viscosity of our sample prior to, you can see a similar viscosity of a similar material from literature. Then if it is low, you use close to 60 mm geometry diameter. If it is medium viscosity such as honey, 40 mm geometry plate dia. High viscosity like caramel, 20 to 25 mm geometry. So, we have to see and study the instrument variables. Okay. We should select the right torque, displacement, speed. Now, our aim is we have to select right torque, displacement or speed, and obviously based on this variable we adjust the geometry selection to get the optimum operating range. So, you have to use your concepts, you apply your concepts and then decide on the torque, displacement or speed. So, in the case of parallel plate which I have just now discussed, the geometric constant in a particular rheometer can be used with this expression R by H. So, we use this equation primarily to convert the angular velocity in radians per second to shear rate at per second at the edge. Okay. So, this angular velocity you multiply with angular velocity. So, it will be radians per second. So, it is overall will be radians per second. So, you get the shear rate in this case if you use the formula. Now, for angular displacement obviously also used for angular displacement in radians per second to shear strain, to calculate the shear strain at the edge. So, either you can calculate shear rate or you can calculate shear strain. So, angular displacement and angular velocity are different. So, you have angular displacement as theta and this is angular velocity this. So, angular velocity theta both you can multiply by c lambda. Okay. So, this will give the shear strain and this will give your shear rate. Now, for Newtonian fluids, to convert the torque Newton per meter to shear stress at the edge, you use this geometric factor C sigma 2 by pi r cube, 2 by pi r cube, where h is the, in this case you require h is the distance between the two plates, r is the the total diameter. So, this is the way Rheometer actually do. Different companies have different Rheometer. So, my part of the talk is, we have picked up some of the company like this TA instruments where they use this particular geometric factors. Now, when do we use these parallel plates? We use parallel plates for low, medium or high viscosity liquids, for soft solids or gels, thermosetting materials, for samples with large particles, long relaxation time. Now, these two are very important. Large particles means you have a particle. So, if suppose it is in this area, okay. Suppose these are the two plates and you have a liquid here. Now, suppose this liquid has this large particles here. So, you should use parallel plate. Then only you will get, suppose if you are using this type of conical type of plate, then there may be some of the particle which may not actually give us right result. So, say the large particles it may be stuck up here. So, in that case your cone and plate may not work. Okay. So, in this, so these are the liquid. Suppose the liquid is here and you use the same liquid in a cone and plate, you get this. So, this is not advised, this is advised for large particles. Long relaxation time. What is relaxation time? Suppose we apply stress or strain. So, you are putting some extra energy into the solution. Now, if you remove this, how much time does it take to come back to its original state? So, that is called relaxation time. So, when it has a long relaxation time, then parallel plate is beneficial. Then temperature ramp. then materials which may slip and small volume samples. For these you are beneficial to use parallel plate assembly. So, the first one is shear stress. So, if you see in the shear stress, the formula is given in this expression, sigma is equal to m into 2 by pi r square. So, if you see lower and lower radius will have higher and higher stress. So, this is what? So, see it is the lowest diameter as compared to this and this will be the highest stress. So, you see this is that particular in the particular rheometer which we are having, this is the particular plate with the radius. So, with decreasing diameter shear stress increases and plate diameter is in the order of 60 to 20 millimeter, fine. Now, plate gap is also an important aspect. Suppose the plate gap is h and a liquid is in between the two plates, this one is stationary. So, you calculate the strain rate here with this expression. So, what is this? This is the angular velocity into r into h. So, it means that with decreasing gap height, so with the height lowering your shear rate increases. So, these gap are usually into the value of 0.5 to 2 mm. So, see it is decreasing. So, this as you lower and lower, so in at this point you will have the highest shear rate. So, it means it depends upon your application, what you want to use. You want to use a high shear rate, you want to fix a high shear rate, you use a lower gap. If you want to use a lower shear rate, you get a higher gap. That is where you could decide based upon your application. Now, there is a concept called as effective shear rate. What is this effective shear rate? For a given angle of deformation, the arc of deformation is larger near the plate's border. So, this is the arc of deformation, this one. So, obviously deformation here, the particles here will be more as compared to the center. So, this is given by this formula dx by dh. So, what is dx? Dx is in this direction, dh is in this direction. Okay. So, the height of the fluid remains constant. So, if the height remains constant, but the distance from the center increases. Okay. So, obviously, if it increases the distance from the center, so if you see at this point, so if this value goes on increases while you go to the border, but dh, if suppose height remains similar at all the places, so it means you have a higher shear at the edges. Okay. This is called effective shear rate. Now, there is another concept called normalized shear rate across a cone. Now, instead of parallel plate, if you put a cone and plate like this way, this is the gap, truncation gap T. Okay. So, this is the height. So, the liquid, so again now the expression is dx by h. So, at the edge you have h which is fixed, and at this end it is dx. Now, this dx is keeping on the reduced gap due to the cone form, the height is closer to the interior. So, at this edge the height is while you go to this center portion, your height decreases. So, it is the least in this point. So, when it is least in this point, so it means that this dx, if I want to write in dx and dh, so dx and dh uniformly decreases as you go from the edge to the surface, is not it? So, dx it decreases in this manner. So, this is from the center portion, and dh also it decreases as you go to the center. Okay, the height decreases as you go to center, and the x coordinate also decreases as you go to center. So, if you take a ratio, this particular property, the shear will always be constant. So, that is why we call, if you use a cone and plate, so it will be normalized shear rate. So, for a cone and plate, obviously the geometric factors will also change. The geometric factor is nothing but sigma 1 by beta. So, it is used for the conversion of angular velocity or angular displacement to shear strain, where beta is in radians. Okay. And what is C sigma? C sigma is nothing but 3 by 2 pi r cube for using to convert the torque to shear stress. Okay. So, this is your truncation height, and so you use earlier case the C gamma and C sigma were different. In the case of parallel plate, here you have a different expression, fine. Now the cone diameter, now this is that cone actually. I am sorry you will not able to see this particular arrangement because it is very difficult, it is the order of 1 degree, okay. So you will not be able to see. So this is a cone plate, this is a bigger diameter earlier. So what you do is you calculate the stress from this expression using the moment of inertia value, you know the R. So you see that as radius increases, the shear stress will decrease. So the plate dia is between the range of 20 to 60 millimeter. So this is what the how the cone diameter decides the shear stress. And in the case of that is cone diameter, now the angle, so this is, see, this is 2 degree, so this particular angle is 2 degree. Now this is 1 degree and this is 0.5 degree, okay. So this, if it is 2 degree, the gap is nothing but 60 micron, this truncation gap T is 60 micron. If it is 1 degree, the gap will vary between 20 to 30. If it is 0.5 degree, it will become less than 10 microns. So it means that you can calculate then the shear rate. The shear rate, what it is defined as, this omega upon beta. So it will decreases with the cone angle increase. So as you increase the cone angle, the shear rate will decrease, okay. So it is order of, usually the cone angle is the order of 0.5 to 2 degrees. This is the cone angle. So you need to ensure that how these particular liquid you need to fill in a cone and plate. So see, this is wrong because you are underfilling it, this portion is not filled up, you are underfilling it, it is underfilled, which will lead to lower torque contribution. This is the right filling because it is going up to the end, you should fill this manner, the right filling, it will give the correct torque contribution, while overfilling you may leak some material outside. So you know this will create a lot of drag force, this drag force will give incorrect torque measurement, it will give additional stress. So this is also incorrect, so this is the correct way of filling the sample in a cone and plate assembly. Other ways you can also calculate, which is the concentric cylinder. What is the concentric cylinder? As I told you, it is used for very low, low values of viscosity. Again the geometric constants changes. So geometric constants given by R1 square plus R2 square, R1 square into R2 square. So angular velocity here again is used, this particular expression is used to compute either angular velocity or angular displacement. Angular velocity you multiply by the, you get shear rate or angular velocity, because from angular velocity you get shear rate and from angular displacement you get shear strain, okay. Then the constant for shear stress is torque, this value 4 pi L, 1 by 4 pi L R1 square plus R2 square into R1 square plus R2. So R1 R2 is this, the inner diameter R1, our exterior is R2. So you insert the sample here, you fill up the entire tube, okay. So length is nothing but this L, 4 pi L, okay. So this is the way you could calculate in the concentric cylinder. So concentric cylinder, what happens? This actually rotates like this. The cylinder actually rotates as this. These are just the arrangement, geometric arrangement. Then you have the double wall cylinders, which is also useful. Here you know it is like this. So this is the assembly, and you have the C sigma and C gamma again taking up the forms, but here you have different values, this R1, R2, R3. So these are R1 inner diameter, R2 diameter with the particular blue, which is the your arrangement where you are inserting liquid. Usually the liquid are filled in this direction, liquid is filled in this direction, okay. So then R3 is also there, R3, likewise R4. So here again you have these different geometric factors, C gamma and C sigma. So you convert torque to shear stress using this C sigma value, and here with this you calculate either angular velocity or angular displacement, either you calculate shear rate, shear strain. So the way you calculate shear rate, shear strain or shear stress. So three things you should notice. One is shear stress, shear rate, shear strain. All this requires actually this C sigma and C sigma value. The previous examples, whatever I discussed, these values will change this correction factor based on the arrangement which you are selecting. So, for this case, in a double wall cylinder, it is used for samples having viscosity less than 1 megapascal per second. Okay. So, I will come to the end of this lecture. So, you have seen that which are the different geometrical arrangements and you use for what purpose. You can use a certain geometric factor for low values of viscosity, you can use something which is higher, something which is in between. The one which I have not discussed is the torsional one, which is used for solid such as steel. So, it works in a different manner. So, we apply stress on both ends, but more or less in the liquid like behavior or those which are viscoelastic, you can use the rheometer for your research purpose to obtain the rheological properties. So, I will stop here. So, you should go through these references for getting the basics of the rheological part. This is the edited book, Rheology of Complex Fluids, and whatever expressions I gave, it is based on the TA instrument manual. And you also follow this. If you are not able to get the book, you can follow this NPTEL course, which is Rheology of Complex Materials, and where you will be deriving many properties which are related to the measurement of shear stress, shear strain, and how you compute the overall stress. All these things are given in detail, which I have not covered in this lecture. So, thank you. So, in the next class, we will start with different types of fluids, which you must be aware, the Newtonian and non-Newtonian fluids. We will see how they are classified and how to interpret data from these particular rheological fluids. Thank you.